There we go. So Andre here is going to tell us that we got the applicative monad proposal in Haskell wrong because he's found a new abstraction to stick in between applicative and monad.
Thank you. Thank you very much for coming to my talk, even though it's so late. I'd like to present the joint work with my PhD student, Georgy Lukyanov. He's at Newcastle University, Simon Marlowe at Facebook, and Jeremy Dimino at Jane Street. I'll start with the beginning. At the beginning, there were no monads, and it was very, very difficult to be a pure functional programmer because you couldn't write programs that make effects in the real world. But fortunately, in the 90s, Eugenia Moji and Philip Wadler wrote these two remarkable papers that introduced the notions of monads into functional programming, and they provided a beautiful way to embed impure computations into pure functional programming languages. Is Phil here? Thank you, Phil. Right. So there's a standard example. It will be an I/O monad in Haskell, where you have an abstract data type I/O parameterized by A, which corresponds to computations, impure computations, that when performed will do some side effects and will return you a value of type A. And there are primitives provided by the standard libraries like getLine, putStringLine, which allow you to create primitive effects. And you can compose these primitive effects using the bind operator. This greater equal operator that takes an I/O of A, a computation that computes a value of type A, and a pure function that examines this pure value and computes the subsequent computation of type I/O_B. So now you can put them all together in the compound computation of type I/O_B. And here's an example, a simple greeting program that uses the getLine primitive and to get the string from the terminal, and then uses a pure function to append hello to it and print it on the screen. So this is very useful and very ubiquitous in modern functional programming. So it even got to the Haskell logo. So we have the bind followed by lambda in the Haskell logo. Of course, I/O is not the only useful monad. And we've just heard from a talk where there was a secrets monad. How cool is that, right? And it's very convenient to program against an abstract interface, the type class monad, that encodes this notion of composing impure computation. So it has this bind operator, now parameterized. It's no longer for I/O, it's for any monad F. And it also has, in addition to bind, it has return, which allows you to embed pure values in the impure world. So forget that they were pure. No. Forget that they were not secret, like in the previous talk. So we can write useful functions against this abstract interface. A function like whenm, for example, which allows you to execute an effect conditionally. It takes two parameters, an fbool, which computes a Boolean value, and the second argument, a computation which you either execute or skip. How do we implement it using this abstract interface? Well, we use bind to extract the pure value from the impure world, B, and then we use a plain if statement to decide whether to continue with the computation Y, or just return the unit, which is the type which has no payload apart from the denoting termination of completion of the action. Here's a simple example of how we could use whenm, right? We can write a program, ping-pong program, that inputs a string, tests if it's equal to ping, and if it is, then it prints pong to the screen. Otherwise, it prints nothing. So here, two example invocations. We execute a program with ping, we get pong back. We execute it with hello, we get nothing back. We can write this program by applying whenm combinator, which we wrote for any monad. Now we use it in the context of the I/O monad. We use the primitive getLine. We turn the string that we obtain into a Boolean by comparing it with ping, and then we, as a second argument, we pass the primitive effect putStringLine pong. It's a very simple example. And monads are great, but they have some limitations. So there is an inherent sequential nature in the monadic composition. Until you complete the first action and obtain the A, there's no way to continue. It's a sort of sequentiality by design. You have to have this value A in order to compute the subsequent computation FB, and then only then you can execute it. If we wanted to have an operator for parallel composition of effectful computations, you would have something like this, perhaps. A product that takes two effectful computations, each producing, one producing a value of type A and another value of type B, and composing them into a compound computation produces both of them. But we cannot express this operator faithfully using the monad abstraction because we will have to sequentialize it somehow. We will have to introduce either FA first or FB first. The second limitation is related to the first one. It again has to do with this sequentiality and these functions that we have. So if we look at our greeting program, it starts with the getLine function. So we can always see the first primitive effect in our computation. But we cannot see any further. We need the actual value name to be able to predict what are the other effects that this computation might perform. And sometimes it is useful to know all the effects that a computation might perform ahead of time. Maybe you would use this information to pre-allocate some resources. Imagine that you knew that your I/O computation is going to do read file on some file. Then you could, for example, test if this file already exists on the disk, and if not, maybe download it from some central repository. So to prepare the execution. You could also check if your execution contains some primitive computations that might fail. So to check whether a computation might fail, and if yes, then how. So there are many scenarios in which you can take advantage of knowing all the embedded effects up front, but you cannot do this with a monadic composition. The functional programming community realized this, and there are a few different approaches to resolving these limitations. And one of the most popular one is applicative functors, which were introduced in this functional Perl by Conor McBride and Ross Patterson in 2008. It's another wonderful paper you should all read if you haven't yet. Applicative functors are quite similar to monads in the sense that they also allow you to embed pure values in a pure computation using the pure method instead of return. And they also have a composition operator that allows you to compose two small computations and form a larger computation. In this case, we take two independent computations. Right? The first one computes a function from A to B, and the second one computes the argument for this function of type A. So we can execute them in parallel. They don't need each other. And then we could combine the results to produce a value of type FB. So what's different compared to monads is that we no longer have any opaque effect-generating functions. We can see statically all the effects before the execution starts, and we can analyze our computations. Of course, we lose something. We gain something, but we also lose something. Because the computations are independent, well, they cannot depend on each other, and you lose the conditional execution. So for example, we cannot implement our ping-pong program, right? Because it has this conditional. The best we can do is we can write a ping-pong program that always prints pong. So there are two effects now. One, you read the string from the terminal and you print pong to the terminal always. Not a very useful program, but maybe still fun. I don't know. Okay, so let's recap. So we've come across a few notions that you might want to express when composing effects, and we've seen two different approaches to this, applicative and monads. So the greeting program, it uses what I call arbitrary dynamic effects. It allows you to execute one effect and then generate a subsequent computation dynamically at runtime. You can do it with monads, you cannot do it with applicative functors. A somewhat weaker notion is conditional execution. Here, in the ping-pong example, we know all the effects up front, but some of them are conditional. Right? So it's subtly different from the first example. Now, applicative functors allow you to express the notions of independence of effects and parallelism. This is something that you cannot do with monad. And also, they allow you to statically see all the effects embedded in the computation. So you can check whether a computation is pure or not. And if it's not pure, you can list all the effects contained in the computation. There's another row here, which was a total surprise to us when writing the paper. We came across another notion that is not possible to express with either applicative functors or monads. And this is the notion of speculative execution. So if you look in the Haxel library, which developed at Facebook to fight spam and abuse in the network, you will come across speculative combinators like this. It's P and P stands for parallel. So what does it do? It executes two computations in parallel, and if either of them finishes early with a false, it cancels the other one because we have no use for it anymore. We know that the result is going to be false. So why can't we express this using monads? Well, because monads require you to schedule effects in sequence, right? And we want to start in parallel. Why can't we use applicative functors? Well, because the effects must be independent. So in this case, you would have to run both of them to completion. So the fact that one of them results in false cannot be used in any way to influence the execution of the other. So this is something we cannot express in either of the abstractions. So in our paper, we introduce a new abstraction and a new way to compose effects, which we call select operator. And it provides a new trade-off in this design space. Right? So it's not as expressive as monads. It cannot express arbitrary dynamic effects. It's not as expressive as applicative functors in the sense that it cannot handle independent effects, parallelism. But it ticks three other boxes, right? So it supports conditional execution of effects and static analysis, and it also allows you to model speculative execution of effects. So interestingly, each abstraction has its own superpower, right? They're all useful. And some applications like Haxel actually use all three. So applicative functors give you independent effects. selective functors give you speculative execution, and monads give you arbitrary dynamic effects. So here is the main slide of my talk. Please remember it. Everything else you can forget. This is the operator we introduced, select. It takes also two computations. The first one computes a value of either type A or B, and the second one a function from A to B. So the first computation selects what to do next. Right? If you've got a left A, you must execute the second computation because you have to produce a B in the end. So you've got an A, you have a function, you need a function from A to B to produce a B, right? But if you've got a right B, you have a choice. You can skip the second computation, right? You don't need the function anymore because you've got a B already, and the function is, in fact, is useless for you. You have no A's to apply it to. So importantly, it's a choice. We don't force the second effect to be skipped. Why? Because we want to preserve the ability to statically analyze computations. So we want there will be some selective functors that will collect all the computations regardless of the values. So we would like to allow both scenarios here, skipping and non-skipping. So with this approach, we still see all the effects statically before the execution starts, because there are no opaque functions here. And we have a limited form of dependence. As you will see, we can implement combinators like when M, which allow you to skip some effects. And interestingly, you can also do speculative execution. So how? You start executing both of the effects at the same time. And if the first one finishes earlier with a right value, you can terminate the second one. So this is where speculative execution comes into play. Well, you still have to list all possible effects in the computation upfront. So no dynamic arbitrary effects for you. So this is a limitation. If you need arbitrary dynamic effects, you still need a monad. Still, you can implement a lot of combinators that are traditionally associated with the monad type class, like when M, for example. So we can implement our ping-pong program using selective functors. We can lift the if statement into the impure world using this if-s combinator. And interestingly, if you can use it to implement this bind operator specialized to Boolean values, which is interesting. So it means, if you think about it, if you can handle Booleans, obviously you can also handle any other enumerable data type. So selective functors are, in some sense, a restricted form of monad where you can only bind to values of enumerable types. Right? So there are many other combinators that are described in the paper. In the remaining time that I have, I would like to elaborate a little bit on the relationship between selective functors and applicative functors and monads. So you could write the function with the type signature of the select operator using the applicative interface, right? You execute both of the effects, and then you've got the either AB, a function AB, you apply the function to the left case, and you've got a B. So do we need selective functors? Maybe not. And symmetrically, we can also implement the apply operator from the applicative functors using select. Well, if you have a function A to B and the argument for this function, surely we will have to execute both of them. So we will just tag the function with a left tag. So it will force select to execute both of these effects and combine them together. So we can use selective functors to implement applicative functors and vice versa. But they're still both useful abstractions. Why? Because these implementations are imperfect. Select A always executes both X and Y, but we introduce selective functors their whole purpose is to be able to handle conditional effects, right? So this defeats their purpose. And up-S forgets about the independence of effects X and Y. So when we write X and Y with the apply operator in between, we know that they are independent. There is no way that they can communicate any information. Whereas if we translate this up-S into the select statement, well, we no longer have this information because select allows effects to communicate in a limited manner. Also, you can implement select operator using monad. Of course, you can execute the first computation, you can get the either AB, pattern match on the result. If it's a left, you execute the second computation. If it's a right, you skip it. It's very similar to the when M combinator, by the way, and you can think of select as being just a typed version of when M. And for many monads, this would be an implementation that you would use. You can define an instance of selective for I/O, where select is equal to select M. Select M is also imperfect, right? So we have to execute X and Y in sequence, so we lose speculative execution, and also it cannot be statically analyzed. So we need all three abstractions. So in the last slide, I'd like to mention some of the applications that we look at into the paper. In the paper, we have two large case studies. The first one is about build system Dune. It's a build system developed by Jane Street for building OCaml projects. And it's interesting because it has an unusual feature. It can report you an over-approximation of all its build dependencies before the build starts, so that, for example, you can run your package manager to install all of them. The second case study, so in the build system Dune, we can use selective functors to model this property, right? Compute the over-approximation of all the effects that a computation might perform before it starts, and then you can still execute it, skipping unnecessary effects. In the Haxel library, there are a lot of combinators that do speculative execution, right? So this p-and, p-or, and there are some other variants. So we can replace them with selective combinators. So we can push some of the code into the library, and we can also use the vocabulary of selective functors to reason about some of the code written in Haxel. There's also an interesting categorization of processor instructions that we came by with. If you think about processor instructions, that some of them simply need one argument, like incrementing a value. And the effect structure is fixed. So you read the value, you increment it, and you write it back into memory or register. There are also some instructions where you need to compose multiple inputs. For example, if you need to add two numbers, you perform two reads, and then you perform one write. And there are also branching operations like conditional jump, right? So in this case, there is this conditional effect, updating the program counter, which you either do or not. And there are monadic instructions where you have things like indirect memory access, where you read the value from the memory, then you interpret this value as address, and then perform a second effect, which is dependent on the value of the first one. So this is like an arbitrary effect. So it's an interesting categorization of instructions. There are also some other applications which we are currently looking into, for example, using selective functors for parser combinators, and a lot more things in the paper. I'd like to finish with this slide with like 3 abstractions with the superpowers, and I hope that you will find a new useful tool in the functional programming toolbox. Thank you.
We have some time for questions. Let's start right up here.
Anything in the way of laws for these type classes?
Yes. So my slide deck is fixed. It's fixed, but there are some conditional effects, right? Laws, yes. Well, typically, laws tell you about how pure computations interact with stateful computations. In this case, well, if the second computation is pure, it doesn't matter if we skip it or not. It shouldn't matter, right? So this is what the first law tells you. The second law tells you what happens if the first computation is pure. And basically it tells you that if you have a complex conditional, where you have multiple things depending on the same pure condition, then you can decompose this into a sequence of conditionals. As long as the condition is pure, it's fine to duplicate the condition, right? And then there's also associativity, which looks a bit ugly, I admit. Basically, it allows you to reassociate the expression. Like with monads and applicative functors, you can reassociate. You should be able to reassociate an expression, a selective expression, to the right. Right? So these are the laws. And if you also have a monad, then we also require that select equals select m at the semantic level, which is similar to up being equal to apply operator.
Yeah. Okay.
You have a question here on Slido. Mm-hmm. I don't understand your speculative evaluation. Even if you don't need the result of the right-hand argument, how do you know you can discard the effects?
Right. Maybe you can't discard the effect. So it depends on your monad. So for example, in the Haxel world, all the effects are reads from the database, so from various data sources. So reading is an unobservable effect. So you cannot distinguish the fact whether you've performed a read or not. So in this case, it's safe to discard the effect midway. But of course, there are situations where it's not safe. So it depends on your monad. So your monad will tell you whether speculative execution makes sense or not.
How about back row over there?
So I'm just wondering, how automatically can we change do notation into selective do or whatever?
So if I understand correctly, the question is about do notation, right? So as you know, we already have an extension for applicative functors. You can write do notation, use do notation for describing applicative computations. And I think it is possible to extend it to support selective computations. So basically, whenever you have a bind, If you are binding on an enumerable data type, you will use a selective combinator instead. So this is something, it's just an idea at this point. If anybody would like to try and implement it, it would be great. I'm happy to collaborate on this.
I have a question here on Slido. Using the Yoneda lemma, we can express lenses as a type which quantifies over functors. Similarly, applicative functors give traversals. What about selective?
It's an interesting question. I've been thinking about it on and off for a while. I don't yet have a good answer to it, but it's something I would like to explore.
Another question on Slido. Can you say more about the underlying mathematical foundation for your proposal? Maybe this is quite similar to the last one. For instance, Haskell monads are based on category theoretic monads.
So this is some sort of a product we have here. Maybe there is a suitable category in which you can explain it. I haven't yet been able to find it, and it's not exactly a product in the sense that this associativity law, it's like a skew associativity. You can apply it in one direction, but not in the other. So it's I've been told that maybe some skew categories can be used here, but I'm no category theory expert. I'd appreciate some help on this.
Let's see, we can take maybe one or two more from the audience.
So that looked like a really cool concept, and I was really hoping to see one of those things so I can use it. So do you have an example? Because we just saw the kind of API, but there was no examples of an actual thing that satisfies the API.
Right. Well, there are plenty of examples in the paper, and there is a library. It's called on Hackage, called Selective. So if you would like to use, you just go ahead, and there are plenty of examples. I can also show you later. I don't think it's worth showing the code right now, but I'll do it.
Any of them are not monads?
Pardon?
And are there examples of things that are not monads?
Yes. For example, there is a const functor, and there are two different versions of const functor for selective functors, and they are not monads.
Monad and not applicative.
There is no such thing which is, yeah, they are applicative functors, but not monads. That's right. Yeah. Mm-hmm.
Okay, I'll invite the next speaker to come up while that person sets up, we'll take one last question.
So I want to make an observation. I want to make an observation, which is that this reminds me very much of the trick in partial evaluation. The trick, if you're familiar with it, it lets you take something that's dynamic but unknown, but has a finite set of values, and make it static, known at partial evaluation time. Now, I suspect you can express that using selective functors in a nice way.
Thank you. I'd like to talk to you about this, Feller.
Okay, thanks very much, Andre.
Thank you very much.